right, good afternoon. How are you? Doing all right? A little ready for Thanksgiving, maybe? Okay, we're going to get going. Today we're going to talk about more than anything else. Now, we will do a refresher. How do we calculate or balance a redox half reaction? So I'm going to remind you of some things you probably learned, probably should know. But mostly what I'm interested in is that you kind of understand and could describe to me, what does oxidation or reduction have to do with, let's say, chlorination, or pipes with water flowing through them, or different environmental aspects, maybe a remediation, like a site cleanup. What does it mean that the ground has not much oxygen in it? What does that have to do with the water in it and its redox potential, its electrical potential? And how would that change if we brought it up to the air, and that type of thing? Like, what is going on with redox? What does it mean when we do an advanced oxidation process? Could you map out where the electrons are going? What is the underlying principle? So that's the kind of the big deal. We're also going to provide that reminder of how we derive the math for it and the thermodynamics using the Nernst equation and Gibbs free energy kind of stuff. So this we should be able to do, or at least kind of go back through some notes and then reason out, okay, here's how we take some thermodynamic data and then arrive at a constant that would describe our reaction equilibrium for some redox reaction. So that's kind of what the aim is today. We're only going to spend one lecture on it, so if you find you need more material, and I'm not planning to go too deep on redox itself, but if you do find that you're more interested, I did cover more of it in some other classes, can share that with you, and the book itself, of course, has a little bit of a deeper dive. Okay, so that's today, and that'll lead us into really what we're describing is the transfer of electrons. Sometimes we might describe it as an oxidant is going to take away electrons for something else. Then the oxidant is reduced. So the language can become a little confusing, but an oxidant is taking electrons. A reductant would be forcing electrons onto something else. Okay, so that's the general sense of it. It can be important in a lot of ways. Maybe the toxicity of some heavy metal in one particular oxidation state is much more or less than another. More commonly, if we think back about our precipitation reactions, the more common relevance is that some species are more or less soluble than others. So if we connect the solubility that we talked about last time to the ability to change the oxidation state of some atom, that can affect whether or not it's soluble. And therefore, if I have something insoluble in my water bottle, it will settle out, and then when I drink from it, I'm not getting so poisoned by that thing, right? So that's quite relevant for those reasons. So these two can be independent, but also are certainly very linked. Of course, rust and oxidation, got some examples here. Rust is essentially, if it's on something that contains iron, that's iron oxides forming, and that is a process where we had some flat surface of iron, and then oxygen starts reacting from the environment, and it turns out that many metals, when oxidized, you get some iron oxides. The iron oxide itself is often takes less volume than just the metal, and so you end up getting cracks and fissures, which open up more surface area for more oxidation to occur, and the corrosion is a self-accelerating process so long as there is oxygen around. Things like water and salts can really encourage that to happen, lower the activation energy for those reactions. Things like that maybe bring oxygen even deeper into the thing. So there are features of our solution that could enhance that. There are other cases where, let's say, aluminum, if you have metallic aluminum, it's very difficult to cause it to rust. In fact, it doesn't rust. And the reason is that that aluminum oxide takes up more volume, more space than base aluminum. So what ends up happening is you do have a very strong reaction to form aluminum oxides, but then it crowds out the space and passivates the surface. Nothing else can grow there. Nothing else can, no oxygen can get deeper than that. So all the zero valent, as we call it, aluminum stays in that state, protected by that passivation layer. So rust, it's an oxidation reaction. So solubility and precipitation go hand in hand. Perhaps we want to precipitate something, so we want to adjust adjust the solubility and then utilize that for the precipitation. There are, and I guess we could also describe precipitation in terms of rain. Rainwater would have some oxidation. The water itself would have some redox potential that we could describe. And of course, all sorts of other natural chemical processes will involve redox chemistry to some extent or another, whether that's biochemical pathways, photochemistry in the environment, photochemistry in our UV reactors, biogeochemical, geochemical, all of this, right? So the advanced oxidation processes that we are coming to, and disinfection in general that we will be discussing, usually we're using some oxidants here. There are some possibilities to do advanced reduction processes. Those are not very common. I don't think we've got many, if any, in practice, like practical, but I know there's some research going on for kind of the reverse. Okay, so that's kind of a big picture where and why we care about it. We'll come back to a few more examples. But first, a reminder, okay, what is an oxidation state? So that we're clear and refreshed here. Well, essentially an atom can be, we have some atomic number, right? And relative to the number of electrons that it would have with zero charge, like let's say I was mentioning zero valent aluminum or iron, we would draw it up like that. That would be zero valent. It has the same number of protons in that atom as there are electrons hanging out. So it's happy. There's no charge. It's chilling. However, maybe sometimes in the environment, certain atoms would like to give or take electrons, and then they'll be stable in some oxidation state where that could be Fe2+, or even Fe3+, right? 2+ being ferrous and 3+ being ferric. So in those states, we are missing a couple of electrons, 2 or 3. And in that sense, our oxidation state would then be Fe2+, or Fe2. So oxidation state of 2 is Fe2+. Pretty self-explanatory. Okay. Anytime we have a pure element, let's say O2, it's in zero valent state, at least as a whole. So iron, pure iron would be Fe, just zero valent. Okay, that's how we describe it. Aluminum, just aluminum, Al, 0, aluminum. We can think of a lot of other allotropes, so to speak. So nitrogen gas, N2, helium is just an atom, right? So our noble gases are just the atom. They are in zero valent states. H2, hydrogen gas, even things like C60. This is Buckminster fullerene, or buckyballs, as some people call them. Or diamond, or graphite, it's pure carbon, zero valent. Okay, so that's kind of the basics. So we can see if we have some ions in solution. Well, sodium likes to be in +1 oxidation state. Quite happy there, and we'll see in a little bit if it's in a zero valent sodium, things can get spicy. Okay, so our certain elements, if they are far away from where they'd like to be, they might be quite reactive. Chloride is often found in a -1, right? Likes to have an extra electron, and so on. Then we can take a look at our polyatomic ions. And it's not necessarily clear, unless you remember a few helpful rules. Okay, well, for phosphate, what's the P and what's the O? Okay, there are some clarifying rules that we can pretty simply identify. Oh, okay, the oxygens must be in this state, and therefore the phosphorus must be in that state. So we'll talk about a few of those But essentially what we're going to do, the first rule of thumb, I suppose, would be to assign the electrons to the most electronegative atoms first. So electronegativity being the most greedy for electrons, fluoride being the most greedy of all, or fluorine. So it's going to be the first one to take electrons, and it's a halogen, so it likes to be in the -1. So we're going to give that the chance to get to -1. Next up would be oxygen, then chlorine, sulfur, and so on. So nitrogen would be more than carbon, and then we could march up the list, and hydrogen would be the least electronegative, right? So most likely to be in a +1. Okay, so that's typically how we assign them. So if we look back at phosphorus, well, we don't have, phosphate, we don't have phosphorus listed here, but if we were to look at a periodic table and recall that electronegativity increases like this across the table. So electronegativity is increasing as you go up, or increasing across or up. Then we would recognize that oxygen is over here, phosphorus is down here, right? Or something like that. And we'll recognize that oxygen is in fact more electronegative than phosphorus. And so we'd give it to oxygen first. So we have PO4 3-. We'll give the oxygens, which would like to be in the 2- state, because they're right next to the halogens, right? So -1 over 1, -2. So this would be a -8 total. And so then to satisfy a -3 charge, we'd have to add 5. Okay? So to get to the -3 from a -8, the P has to be in a +5 state. So each of these, this would be 4 times -2. Okay, so 5 minus 8 is -3. Okay, so that's how we would proceed with this. Now, anytime we add a proton, if you recall, phosphate can protonate. We can get phosphoric acid and such. If we add an H, so it's HPO4 2-. Well, what have we done? We've added one hydrogen that has a +1 oxidation state. And that we'll just leave it as a +1. It's not going to affect the oxidation state of those guys. Okay, so those are some helpful rules. We could do these same types of procedures with these other guys to identify what is the oxidation state of any one atom there. Okay, so we'll lay them out a little more explicitly here. So for monoatomic, obvious. Let's see, let me just double check. Okay, occasionally you'll have only one oxidation state. For some, there are many. A lot of the transition metals have plenty of oxidation states they could occupy. Okay, so for if it's monoatomic, already talked about that, but pure oxygen, pure carbon, something like that, it's either 0 valent, or perhaps if it is a charged species, H+, there you go, as in a +1. Except for metal hydrides, they're not too common. H-bound is just going to be an +1. Okay, so we don't really treat that, treat hydrogen as anything but a +1 state. And by the way, you'll see these often written as, instead of the plus, you might just see the Roman numerals. So Fe with a 2 Roman numeral, that is saying it's in the +2 oxidation state. Okay. So if we then, this could be a part of some other molecule, but if it's just by itself, it would be Fe2+, right? Okay, so oxygen with a -2, talked about that. That's in almost everything, but there are some exceptions. So if we have peroxides, it's the OO group, essentially those guys, and it's peroxide, that per is essentially telling us that this is actually not in the -2 typical state, this is in a -1 state. So peroxide, let's say hydrogen peroxide, H2O2, you could also describe water as dihydrogen oxide, right? And then you have 2 hydrogens, 1 oxide, oxide being a -2, something described as an oxide is going to indicate it's a -2, but if you have peroxide of some sort, now we have +1 and a +1 from the hydrogen, and so we need a -1 and a -1 from the oxygens, right? So peroxides have that exception. Okay, so then covalent compounds, oxidation state of each atom is the charge remaining when each shared pair of electrons is assigned completely. I think this one's kind of obvious. Sometimes bonds can share electrons, but the net charge for some molecule is the net charge. Okay, the sum of oxidation states when an atom is in a multiatomic substance is 0 for molecules and equal to the formal charge for ions. So if it's just some neutral molecule, it's 0, obvious. Charge for the ion, we already talked about that. Okay, if we have multiple atoms of the same kind occur in a species, which is pretty common in carbon, organic molecules, you could have tons of different carbons in different places with potentially different oxidation states based on what's around them. You could describe that as an average, or in some cases, I guess, maybe we would narrow down into one particular spot, but you could also give it a fractional value. And so if we had to describe something like phenol, on the whole, we might assign some fractional value. Okay. So with that, we kind of have the basics, the rules of thumb. We could take a look at all sorts of environmental compounds that we might find, and then look at and derive or discern what their oxidation states of each atom there would be. So some of the perhaps interesting ones might be the nitrogen compounds. Deal a lot with nitrate, nitrite in environmental systems. So we could start with nitrogen gas, N2. Obviously that's 0. Could go on N2O, this is nitrous oxide. We'll see that the O has to have a -2, and therefore each nitrogen is a +1. Moving forward, we could go to nitrite, NO2 minus. Well, if we have 2 O's, that's a net -4. We need a +3 to balance it back up to -1. So we have nitrogen in a 0 valent in N2. We have nitrogen in a oxidized state in our laughing gas, nitrous oxide. And then if we go to nitrite, we have a negative state, right? This is more reduced. So if nitrous oxide is more oxidized than N2, nitrite is more reduced. We could also have NO2 gas. We'd find that's +4. And nitrate would be a -2. Excuse me, I said -2, sorry, I meant +5. Okay, that's what. So we could go through each one of these. We could check them. This is something that you should probably have done before, probably should be able to piece together and recognize. And it becomes important when we want to understand if we're saying we're going to oxidize something. Well, how many electrons does it take? How many chlorine molecules do we have to consume in order to achieve that? A very common example would be if we are treating water that has sulfide in it. Perhaps we're taking it from groundwater and we're adding chlorine. Well, some of the chlorine will react immediately with the sulfide, and the oxidation power will be spent. This would also be true of other metals that are oxidized easily by chlorine. Suddenly, a lot of the chlorine experiences what we call instantaneous demand, and it's gone. It's oxidizing, spending its effort oxidizing things, so we could then calculate, given some amount of sulfide, how much extra chlorine do we need. So there are reactions like that we see pretty commonly that can be quite important. On the flip side, sometimes we want to get rid of chlorine before we discharge some, let's say, an Olympic swimming pool. There's a lot of chlorine in there, and it's like 1 million gallons. If we discharge that, it's like 1 million gallons per day of a flow, or more, if we discharge it within 1 hour. So that's actually quite a large flow rate with quite a lot of chlorine. Represents a very large hazard for the environment, so we might have to add a bunch of sulfide or thiosulfate or something that's a reduced version of sulfur to consume that chlorine. And what we would find is if we're going all the way from sulfide, it takes 8 electrons to get sulfide to sulfate, and therefore it's going to consume 8 molecules of chlorine. Because when we look at that, we'll see each free chlorine is essentially going from, we're doing a 1 electron transfer for it. Okay. All right, so how do we describe redox reactions? Well, we will split a reaction in half so that we can handle the reduction side and the oxidation side. So we will do half reactions, and these will be equilibrium systems, although some are so extreme that there's never really going the other way. But we do describe them as equilibrium. So the half reaction lets us kind of track it, and we would take a reductant is yielding an oxidant plus an electron, or an oxidant plus an electron is yielding a reductant. At the end of the day, when we combine these two reactions, these two half reactions, we get no net electrons that are visible. The oxidation states change, and the electrons help us track that in the half reactions, but on the whole, we're not producing or consuming electrons. We don't describe our chemistry as if electrons are out in solution exactly. Okay, so when we manage the half reactions, we do have to describe that in a sense, and that's mostly what we're talking about today. But electrons, it's not right to think of them as free-floating in the environment. Okay? So if we want to put them together, we could say a reductant plus an oxidant is going to give us, reductant 1 plus oxidant 2 will give us now, if the reaction proceeds that way, now what was a reductant could now be considered as an oxidant. It's a little, not the simplest way to look at it, but the oxidant will be reduced, the reductant will be oxidized, is the point. There's a little mnemonic that you could remember if you wanted to. Oil rig, oxidation is loss, reduction is gain of electrons. Okay? All right. So how do we go about setting up and balancing a half reaction? Well, we have a nice set of 8 steps we can follow. First of all, we have to identify what's the oxidant, what's the reductant, and how we are describing each half of the reaction. So we then would, by convention, we write the oxidized form of each half on the left and the reduced form on the right. For each of those half reactions, then we balance for atoms other than H and O. Then we balance O, and we do so by adding water. So this is a redox reactions in water, by the way. Then we balance H by adding enough H+. Then we balance the charge by adding enough electrons, which, by the way, should, once we account for the stoichiometry, that should account or match the change in oxidation state. Okay, then we can double check that everything's balanced and add them back together. When we do, sometimes we'll have to just make sure that, maybe we'll have to multiply by 2 or 3 to get the stoichiometry correct so that the electrons drop out of the solution or drop out of the equation. Okay, finally, so the final step, that's when you subtract one half from the other or add them together however it logically makes sense to do, right? You don't want to end up with twice the amount of electrons on one side because you accidentally subtracted when you added. but you flip them around such that when you add them together, the electrons are gone, cancel out. Sorry about that. Okay, so that means you would subtract reduction half from the oxidation half reaction, or you could flip that to be reduction to oxidation and add the two together. That'll be intuitive when you see that. Okay, so what would this look like? Let's try it out and balance manganese oxidized to manganese dioxide by chlorine, by Cl2. So first thing, you'd want to write up two half reactions, the oxidized form on the left. So see what you can do with that. Probably be good to start with what are the oxidation states of each atom in these pieces. All right, let's get most of the way there. So we'd probably have to flip back to recall, but there's a couple things to do. First of all, listing the oxidized version of each species on the left. So we'll go ahead and start with the manganese oxide. And if we take a look, with 2 oxygens, that has to be -4. So the manganese has to occupy +4 to account for that. That is more oxidized than a 2+ state. It's a more positive, so we're going to put that on the left. Then if you noticed while I was writing this up, I went ahead and just put Mn2+ on the right, and I left myself some space in case I needed to add stuff. And that's all I did so far, and then I went to think about chlorine, and I said, okay, we've got Cl2 here, and I'm going to go ahead and say that's probably the oxidized version, or the oxidant version. And if you recognize chlorine, well, chloride is a happy state. Chlorine likes to be in Cl-, right? It's always in that form, almost always in that form when it's like hanging out in water. So Cl- is probably what we're getting. It's a good assumption when we do some sort of oxidation. So some sort of free active chlorine is probably going to Cl-. And we need 2 of those because we've got Cl2. Okay? So that's what I did. Balanced that. Then I went back up to think about my manganese equation. The next step would be to balance. So we balanced everything except for oxygen and hydrogen. Then we balanced oxygen by adding water. So we had MnO2 on the left, so we need 2 oxygens on the right due to waters. Then we need to balance the hydrogens. Well, we have now 4 on the right, and that means we need 4 on the left, so 4H+. And then we need to balance the net charge to make sure the charge is the same on both sides by adding electrons. And so on the right, we have a 2+. On the left, we have a 4+, so we need to add a couple of electrons. And if we stop and think about it, we went from a 4+ to a 2+, so we kind of could have just guessed in the first place that we were going to be adding 2 electrons somewhere. Okay, so that's how we split that up and say, okay, now we have MnO2 plus 4H plus 2 electrons is yielding us Mn2+ and 2 waters. Okay, so that's half the reaction. Then we go to the chlorine. Again, we kind of have to recognize Cl- is going to be a part of this. We were only told that we're oxidizing manganese 2+ to MnO2 by chlorine. That was the only thing we were given. Okay, so that one, we balanced the chlorines already. Just add the 2 charges to get the 2- on the left and the right, and we should be good. Okay, so at this point, we can rearrange to write it out according to the way where we're going to make sure that the electrons are settled. And perhaps in a way that makes sense in terms of we are oxidizing Mn2+ to something by adding chlorine. So that's the way I like to look at it. I want to say, I want to have chlorine, Cl2, on the left side of my combined equation. So let me go ahead and do this. I'll say on my combined equation, I want Cl2 on the left side, and I want manganese 2+ on the left side, and whatever goes with them. Okay, that's how I like to think about it, because chlorine is oxidizing Mn2+ to yield some product. So that's the way my brain works best. Thing right here, it's piece, plus this side, so that'll be plus Mn2+ and 2 waters, is going to be, and this is an equilibrium reaction when we put them together, and we will have 2 Cl- plus MnO2 plus 4H+ and 2 electrons. So with all of that, the 2 electrons should cancel. Verify that. We're good. We can also double check to make sure everything else is balanced. 2 chlorines on the left, 2 chlorines on the right. Manganese on the left, manganese on the right. 2 waters, so that gives us an O, so 2 oxygens and 4 protons, and we also have 2 oxygens and 4 protons on the right. So everything's looking good. Our final reaction should be Cl2 plus manganese 2 plus a couple waters on the left and a couple chlorides plus MnO2, manganese oxide, I guess, and 4 protons. So one thing we'll often see in redox chemistry is there are many cases where we have some change in acidity, right? We're consuming or releasing protons as part of the deal. Okay, does that make sense? Good on that?
So another way to think about this is, maybe is it right to say the 2 electrons needed for oxidation of manganese is coming from the chlorine?
Yeah, so essentially the electrons that were on the chlorine, well, no, not on the chlorine. The chlorine took 2 electrons away from the manganese 2 plus. So each chlorine atom took 1 electron because they went from 0 to -1, and that means they were oxidizing, taking electrons, becoming a little bit more reduced. And the manganese was becoming more oxidized to MnO4. That's exactly right. So then you could consider the same type of reaction. So if you want a little more practice, you could do the same thing with OCl-. What you'll find is a very similar equation. And just a side note, it turns out that when Cl2 gas, when you put it in water, it reacts and you get, well, ACl- and an OCl- plus some acid. So it turns out that when we add chlorine gas, Cl2, we are essentially making free chlorine. That's one way to make it. But I'm going to set this side note aside. Don't think too hard about that. Just wanted to highlight it's going to be a very similar process. So if you take OCl-, this is the deprotonated form of our free chlorine in water, then you will find a very similar situation where you need 2 of these active chlorine atoms, and you'll notice the oxygen is a -2 state, and that means the chlorine has to be here in a +1. Okay, so when you then change that, you will be giving that this chlorine will be taking electrons, right? Okay, so feel free to try that on your own at some point. All right, any other questions, issues on that? We good? Okay, so a few more examples, nature or otherwise. If you've gone like tromping through the woods or through near a creek or something, you saw this like orange gooey stuff oozing out of the ground. It looks kind of like straight up pollution out of some toxic landfill or something. That's actually just a natural process. That's iron reducing bacteria solubilizing a lot of iron in whatever groundwater is nearby. That's coming up to the surface, and then it's oxidizing by exposure to the atmosphere. And so then you're getting this ferric chloride, iron, not ferric chloride, oxides. So you're getting iron oxides, which look like rust, which are that color, and essentially you have a rusty colored water. And it's associated and probably attached to a lot of bacteria that were making use of some redox chemistry, making use of the fact that they could manipulate the electrons with iron to make a living. Okay, so they are then forming a bunch of iron out in solution. Then it's becoming less soluble, precipitating, and all of that. Okay, so oxidized forms of iron and manganese are highly insoluble, and that's kind of one feature here. They're soluble when the reducing bacteria were reducing them, solubilizing it, then they reach the atmosphere, they're oxidized, becoming insoluble. So then they're precipitating. That's the deal. That's not necessarily true of all metals or all situations, but for some, like iron and manganese, that's a good general trend. So when we treat groundwater for a variety of things, we are often employing some oxidation. So if we're trying to remove arsenic, so iron and arsenic kind of go hand in hand, both of them follow that trend. Even trying to remove manganese would be similar. If nothing else, to add oxygen to the water so that it's more palatable. So we are adjusting the redox potential of the solution by adding oxygen. Typically, manganese requires a little more, maybe some stronger oxidant or some catalyst to help that. But that's kind of what you can see. And little graph here, this is a removal of iron by oxygen in some solution at various pHs. So if you recall from last time, we could see that pH had some relationship with our oxidation reduction potential. So if we check this at a pH of 7.2, the speed at which we are removing iron is quite fast. As soon as we bump the pH only down to 6.6, we have made the solution more acidic, and that's changing the proclivity to oxidize, right? So this is so it's much faster to oxidize at the higher pH, much slower at the lower pH, and therefore small shift, but now we are removing the iron much more slowly. Okay, some other applications, and that's, those were kind of iron, manganese removal, would include arsenic applications. Some other applications of using oxidants might just simply be changing the color of our water. So there's, yes, color, but I was coming back to that. It's taste and odor. So we can have various chemicals. Sometimes, it could be hydrogen sulfide. Already talked about that a little bit from groundwater. But it could be other stuff. There's a molecule that is known for kind of a slightly gross earth type of taste, geosmin, I think that's how you spell it. It's just known as something that kind of tastes bad, and it's naturally in the water sometimes from exposure to earth and soil, stuff like that. So maybe you want to degrade that particular molecule. Maybe it has no impact on health, not much of a thing, but it kind of smells or tastes bad, right? So a lot of times we'll apply some oxidant to try to transform those molecules, see if we can mineralize them or at least transform them in a way where they are no longer a bother. Of course, sometimes we could often use activated carbon like we talked about before. So an oxidation approach would be kind of an alternate to that. Little picture here. You can imagine what may be happening here is adding some bleach to these different food coloring vials, and it goes down and gets a little mixed. There's still a little bit of food coloring on top that doesn't have a lot of bleach, and it's bleaching the colors. I think that's what's happening there. I have a link there too. I'm not sure what that's to do with. Maybe it's to do with that. So maybe we'll take a look at that in a few minutes. Okay, color. Speaking of color, you know that natural water can have a wide variety of different colors, right? Sometimes it's crystal clear, sometimes it's brown and muddy, sometimes it's somewhere between, blue, green, whatever. I took all these pictures except for that really pretty one at the bottom right. Okay, so if we have iron or aluminum coagulants, sometimes the change, an oxidation process could actually change the natural organic matter and improve or hurt its ability to coagulate. So sometimes the color removal or some oxidation helps or hurts coagulation a little bit. I think in general it tends to help it, but it kind of depends on the nature of the organic matter. If you're using an oxidation process to try to remove just generic organic matter, and there's a lot of organic matter, you do come into some potential problem of disinfection byproducts, especially if you're using some halogens or if there's some halogens in your water to begin with. Introducing a highly oxidizing environment could cause the halogenation of molecules. So we often talk about haloacetic acids or trihalomethanes, THMs. These are trihalomethanes. If you have any organic molecule, we'll call it R, some organic molecule, with an attachment that is a methane type attachment, a methyl group, normally has 3 hydrogens, but if you put it in a highly oxidizing environment and you have halogens around, maybe they want to steal those electrons from the hydrogens and substitute themselves right in place. And so then you end up getting things like the carbon with 3 halogens attached. So 3 chlorides or bromides. So in seawater, you will get potentially tribrominated instead of just chlorinated. In any case, those things are not so good. They can be carcinogenic, toxic otherwise. We don't want them. So there are some considerations there, but it can do some things. And again, this is some random schematic of a potential organic matter molecule, right? They can be very large. Who knows what all's in them? Who knows how they're going to break apart and what parts might be toxic? There's a lot of questions there. Okay, here's where I meant to talk about the coagulant aid for the oxidation, but already mentioned that. Okay, now kind of touched on this a little bit, but in addition to the taste and odor stuff, sometimes we are specifically concerned with a pharmaceutical or something like that. So if we wanted to, let's say, treat industrial wastewater to get rid of residual dyes in a process water, or we're treating municipal wastewater and we don't really want to discharge any heroin or caffeine or antibiotics to the rivers and waterways because people that may be consuming such pharmaceuticals and drugs, they're going to excrete them when they use the restroom, right? So that's going to enter the waste system, and so it's surprising to talk about heroin or something when you first hear it, but people are using all sorts of chemicals and will be excreting therefore all sorts of chemicals in their degradation byproducts. And so how do we deal with them? Well, one option would be to use some sort of oxidation process to try to transform or even mineralize them. Mineralizing meaning we're taking them to CO2, some inorganic form of these elements. So CO2, nitrogen, gas, and things like that. So in this example, there was a photofenton process, which is basically taking hydrogen peroxide plus some iron. It catalyzes the formation of hydroxyl radicals, which we'll talk more about, but these are extremely reactive. They're effective at reacting with all sorts of stuff, and they go away very quickly, therefore. And so they're extremely oxidizing and can destroy things like acetaminophen in this example. Okay. So less common, as I've said before, it would be some sort of advanced reduction, or just in general reduction processes. Reduction processes themselves are around, but not as common for water treatment, because usually we're in a more oxidizing environment. But there are some examples. I mean, even chlorine quenching, that's a reduction process. Mentioned that already because the chlorine is going to oxidize that thing. But in this case, when we're trying to remove the chlorine, we are adding something that is a reductant to oxidize or to take away the oxidizing power of the chlorine. Sometimes we might add, for example, zero-valent iron to help dehalogenate chemicals in the groundwater. So if we had some halogenated contaminant, things like, you might have heard of things like TCE, trichloroethane, from often find these in like leaky storage tanks for dry cleaning and things. So dry cleaning, by the way, we're using solvents that are just not water. So when you take your clothes to the dry cleaner, if you never thought about it before, how do you get something clean when it's dry? It's not technically dry, it's just not water that you're using as a solvent. You're using some other solvent, and if you've ever worked in a lab and played around with different solvents, you'll recognize, oh, that's a lot of chemical of something that's potentially hazardous. And so things like trichloroethylene or ethylene, that would be a molecule looking like this with a hydrogen and 3 chlorides, and like that. Well, it turns out if that's in the groundwater, we don't want it in the groundwater. It's hazardous. Well, how do we treat it? Well, one thing is we might be able to reduce it using zero-valent iron, which would like to oxidize. So it would be happy to give away an electron, which would help this convert and dehalogenate. Okay, so that's one other example you may have heard about or potentially worked it. Sounds like it looks like you've Cougar. If you have some examples.
Yeah, we did an injection job in New Rochelle, New York.
Okay.
So it was kind of a cursed project because they wanted the zero-valent iron gravity fed into fractured bedrock, which was really difficult.
Sounds like you might need a little more pressure.
Once it gets in those pores, or in the fractures rather, the formation is going to take it. That was pretty cursed.
Yeah, very interesting. Yeah, so it's used sometimes. Groundwater is a little more common because at the surface, things are just going to be exposed to so much oxygen that you'll have a more oxidizing environment. It's maybe harder to make use of a reduction process. Okay. Sometimes metals are less soluble in a reduced form, so maybe we want to do that on purpose. I had somewhat of a harebrained idea for a proposal not too long ago where a lot of times we do a photo-oxidation processes, and I was thinking to myself, well, maybe we can do photo reduction if we have some wastewater that's been processed in an anaerobic environment. So I have a colleague, actually, this guy here, has some cool anaerobic wastewater systems that produce pretty high quality water, but they've been in an anaerobic process, so they're probably oxygen deprived. So the concept there was, which maybe I'll try again and get funding one day, but the concept there would be, hey, can we do what we normally do with photo-oxidation except make use of the energetic electrons to do a reduction process instead? Because there's no oxygen around, could we harness it that way? So maybe there's some interesting things that could happen. Okay. All right. So back to the thermodynamic aspects. Wanted to kind of tie back in. We know something about these half reactions. We know something about, oxidizers are important for this. Reductants are important for that. Well, how do we describe it mathematically? How oxidizing? How reducing? And so usually what we're aiming for is to kind of describe the activity of electrons, even though we're not treating them as floating around in solution. It's like, how much potential is there for activity of electrons to be transferred? So, mentioned this already, but we don't actually treat electrons as if they exist in solution, but in half reactions it's convenient, and we'll simplify it in doing so. So we've already talked about the structure. We put the oxidized form on the left, plus some amount of electrons to get a reduced form on the right. And then we can describe that equilibrium by some constant, equilibrium constant, with the, in this case, again, it's products over reactants, but here's where the convention is a little different than in some cases. We'd have the reductant on top divided by the oxidizing species. The A, by the way, this is activity, and oftentimes, so A is activity. If in a dilute solution, this would be just simply that. So the activity of something would be the molar concentration of it. Now, in truth, it would be, we'd have some correction, some gamma correction value for that. So we could say the activity A of X would be written that way and would have that correction activity coefficient, which we could calculate. There's a few ways to do that. Just, this is the concentration, okay? That's the point. So we could go into more with all that. Okay, so, but how do we know the concentration of electrons, right? We don't really have a measure or a handful of electrons, okay? So then that gets us to the situation where, and especially because they don't sit there and stay there in solution, we really need to have some way to deal with them on the half reactions. But we can't isolate a half reaction in total. So we actually need a reference point to begin with, and that's where we start by convention by looking at the half reactions or the total reaction, two halves of hydrogen gas in equilibrium with H plus and electrons. So this one is kind of our overall reference point, the standard hydrogen electrode or the standard hydrogen reference point there. And we define this as the K for this guy is 1. We just call that 1, okay? Which means that is a nice reference point. We'll come back to that and kind of list the standard electrical potential for that reaction is 0. It's our baseline. We do that because we have to have some reference point, because each of our half reactions is in reference with the other half that is happening. And if we take all of the chemical reactions in the world and they all depend on one another, we have to have a reference point somewhere to make any sense of it. It's just the way it is. We have to have it. Okay, so back to the activity of an electron. Using this convention, using it that way, we could actually do some calculations. So if we have some activity of the H plus that we just talked about, that K value, we define that as 1, we could find the activity of an electron. So we know we defined this part as 1, well, excuse me, the K as 1. Then we are given an example of a system at pH 7, so H plus is 10 to the minus 7, and with some amount of H2 gas present. That gives us a value for our activity of H plus, H2 gas, right here. That with the H plus here, we can actually calculate the activity of electrons for that particular system is 10 to the plus 4.5. Okay, so we could plug things in there given these conventions. Of course, we could also use the P as a log function, pH, px. In this case, we could say Pe is negative 4.5. So similar to the pH scale, we'll have a Pe, and here we have a value for this system, Pe is equal to negative 4.5. So that would be the negative log form of the activity of electrons in that particular case. Okay, as we know, been talking about this, the amount of redox potential changes with solution, with what's in the solution. So in different solutions, we'll have different values of our electron activity. And once we know that, we can then go forward and find equilibrium with other reactions. So for example, the equilibrium between Fe3 plus, ferric iron, and electrons going to Fe2 plus, ferrous, we could define that in relevance to other pieces because we know the activity of that electron. So if we find the activity of the electron in a given solution, it's again why pH matters, then we can plug that in and account for it in other systems. Okay, so that's quite handy. We can take take from here, or maybe we get it, and then we plug it in there. All right, so we measure this actually quite often. We can have a redox potentiometer. It's probably not called that. we measure the electrical potential, and we call that EH. Got a question? Yeah.
How are we able to substitute the pressure with the activity? Is there a reason?
Yeah, the pressure here, that's a good question. There's a chance that I transcribed this incorrectly, and that should have been molar units. And there's also a chance that there was some assumption made there in the book. So I'm not exactly sure. So we'll have to come back and check on that. If we go to that spot in our book, this is our primary book. I have taken some spots from some other book. This is the one that we have been using. We can check in, and there's probably an explanation or perhaps a mistake of mine there. Okay. So, assuming we get that right, we can take measurements with some potentiometer, get this electrochemical potential, EH. We'll come back and take a closer look at this equation, but it is factoring in some pieces like the ideal gas constant, the temperature, and Faraday's constant, and relating this electrochemical potential to the PE, okay, to this negative log of the activity of the electrons. Okay, we typically will measure this in millivolts, and this is kind of where we can get the so-called standard electrical potentials if we were to put the system in standard conditions, 25 Celsius and so on, and we'll get these PE naught values, these standard potentials that we'll take a look at. We'll come to the table in a couple minutes. I wanted to just comment before we get there on some of the more common or a couple of simple scenarios. I already talked about that convention. The convention will come back and be a little bit interesting as we develop our Ks in a minute. So, in terms of thermodynamics, our tendency is of some reaction is driven by our standard electrical potential, E naught. We describe that in volts typically, so a few examples would be oxygen with electrons and hydrogen. This will have a strong tendency to form water. Okay, it's not very likely to come to the left, so that is a very positive reaction. So if we ever put oxygen and hydrogen together, they're very likely to form water. Chlorine plus electrons, very likely to form chloride, Cl-. Even talked about that earlier, basically. And the standard electrical potential would be 1.39 volts, very likely. The hydrogen half reaction, right? The H plus an electron going to half of H2. This we have defined as 0 for the standard electrical potential. That's our reference point from everything else. We can find everything else from that standard. On the flip side, sodium plus an electron does not want to go over to 0 valent sodium. In fact, it would much rather come the other way. So this is, if we have sodium in the 0 valent state, it's extremely likely to come back to sodium plus. Okay? And that's why we get metal fires, by the way. So we might have to wait for next time to come back to this, but I have some fun resources to share with you about that. Okay. A couple other details here to consider. So typically under standard conditions, we are treating our the activity under this standard, when we say standard potential or our standard references, we are assuming the activity is 1. And if we are in a dilute solution, say dilute here, if it's in a dilute solution, then it's 1 mole per liter of a dilute dissolved solution. Okay, already covered this part, why we define the hydrogen half reaction as we do. The standard electrical potential doesn't actually depend directly on the stoichiometric coefficients, whereas our Gibbs free energy does. So it's a little different there, but otherwise it's a pretty similar setup. So when we have a higher standard electrical potential, the reactant is usually a stronger oxidant, is the way we could look at that. And lower, it's usually a stronger reducing agent. Okay, so if we compare two molecules and look at their standard electrical potentials, we could see which one's a stronger oxidant or reductant just by those standard potentials. So we might look at oxygen and chlorine gas, both strong oxidants, and we could compare which one's stronger in terms of oxidation potential. Sodium metal spontaneously ignites in the presence of oxygen, so that's fun, or especially with water. But I want to talk a little more about this stuff before we come back to that. So another thing we can do for experimentally discerning what's going on and identifying, isolating these half reactions is to use an electrochemical cell. So we will often see, even from some very simple chemistry or a car battery, there are many electrochemical cells out there. And what we can do is set up 2 basins that allow for us to do both half reactions quasi-isolated from one another. Now they are connected, but we can then measure the flow of electrons from one solution to the other, and do so using 2 electrodes, a cathode and an anode, connected with a potentiometer between to observe the flow of electrons, and we use a salt bridge to allow the flow of the salts to go back and forth to accommodate for the electrons that are going in some direction. So this is an electrochemical cell. This is also a battery. That's how you could describe it. And so if you can reverse the direction by applying some current, then you are recharging the battery. It's just, you have to make sure that the salt can flow and readjust accordingly and efficiently in order to make that happen. So the way to describe this would be the electrical potential of the entire cell would be that of the cathode minus the anode. And there you have it, okay? The anode is what we typically show as a negative lead. That would be where the oxidation half is occurring. Whereas the cathode, we have the reduction half. So maybe one way to think about that would be the cathode is going to be donating electrons and becomes positive, okay? Whereas the anode is going to be taking electrons and therefore becomes negative. Okay. All right, so then probably just summing it up the way I just did here. Yeah, there you go. Now, when we combine these 2 reactions, this is essentially combining, just like we did in the past, the 2 half reactions. And so we can look at it in terms of electrical potential, in addition to looking at just simply the balance, right? So we looked at the balance already. Now, in this particular example, if we have copper and electrons going to 0 valent copper, standard potential is plus 0.34. Whereas zinc plus electrons going to 0 valent zinc, that is negative. So what we know is that the copper is likely to go to the right. The zinc is more likely to go to the left, okay, in these 2 reactions that we drew up. So if we have copper 2+, plus zinc, yielding copper, 0-valent copper, and zinc 2 plus. If we add these two equations together to get that, so this on the left, and we are going to just flip this guy around and add them together. And again, we come back to what I was saying earlier, something acts upon something else. If Cu2 plus is going to oxidize zinc to form Cu0 and zinc 2 plus, we add our equations accordingly, right? In this case, the example is subtracting this half reaction. So that's why we have the minus here. So when we add it together, we get a net cell, electrochemical cell potential at 1.10 volts. And this is, so it's a positive E, and if we were to calculate it, it's a negative delta G. That means it is favorable and driven by this electrical potential. So it is a favorable reaction. If we flip it around, we essentially reverse the electrical potential, and now we've reversed our standard Gibbs free energy. That's positive. So we would have to push it to go that way. We'd have to, for example, act like we're recharging a battery and put a lot of energy towards reversing it. So we can see how and why these electrochemical cells can work based on all that. Does that make sense? Good. Okay. I think this is probably the last little bit I want to cover. And again, just kind of a overview here. I don't really want to dig deeply into every last derivation. You've seen this stuff before. This is Gibbs free energy stuff. This is thermodynamics. We can start with a Gibbs free energy, and we can define that based on the, for a cell, for an electrochemical cell, as the number of moles times the Faraday constant times the electrical potential of the cell. We can break that out into the Gibbs free energy of reactions instead of just the standard. And this should look a little familiar. It's the standard plus RT natural log of K, where K is that ratio of activity of reductants over oxidants. If we divide by negative n times the Faraday constant, we can simplify this, kind of addressing that right there, and convert this into the electrical potentials. So we'll end up with this guy, which substitutes, and we get the electrical potential is the standard electrical potential minus RT divided by n Faraday times natural log of K. So the deal is, conventionally, we have this negative here, but then we can convert it to a positive because this was described as reductant over oxidants, but we can flip that and get this final form over here with a plus, and we simplify that R, so the 2.03 RT divided by F, we can just simply calculate that into 0.059. So that's why we get this, or it shows up in our other book like this. Okay, so my point here is just that we can go from our thermodynamic principles, do a little bit of adaptation according to how it works with electrochemical cells, and get a nice usable equation that looks quite a lot like our Gibbs free energy calculations, which you've seen at some point. And we can describe our EH then in terms of PE and some constants and temperature. Okay, so that's kind of the big picture view there. We could also take a look at all sorts of half reactions, their log Ks, the PEs, and so on. Okay, I think just going to end it there. We'll pick back up, talk maybe just a little bit more, or watch a fun video if nothing else. All right, we'll see you guys on Tuesday.